So today we're going to continue on our last video on this cubic identity to to look more on the second rule that I explained to you guys in the beginning of the first video. So yeah, we're also going to look at this too. So we're just going to look at both of these today. And this won't be as magical as this, but it'll be really useful. It'll be providing really useful information though. So yeah. So the first problem we're going to do today will be, let's put this in blue. So given that x, y, z are positive integers specifically, positive integers, and x cubed minus y cubed minus z cubed is equal to 3 times x times y times z, and x squared is equal to 2 times y plus z. Then find the value of, this is a pretty long expression, it's actually not that long, 5 times xy plus y times z plus x times z. Okay, so find this value. Okay, so this expression looks pretty complicated, but actually all we have to find is just these values and the values of x, y, z, and that's it. And yeah, don't really worry about this expression in general. It's just in this format so that you get a nice answer. But yeah, so first, just pause the video and have a go at this problem first. So the solution is, let's start. So x cubed. So in the previous videos, we were given that a plus b plus c was equal to 0. And then from that, we got a cubed plus b cubed plus c cubed is equal to 3 times a times b times c. But then this time, we're given that, so here, basically, this is equal to x cubed plus the cube of negative y plus the cube of negative z. And then the product of x, and then this is basically just 3 times x times negative y times negative z. The negatives become positive, so it's just positive here. So here is saying that if we let a equal x and b equal negative y and c equal negative z, then here is suggesting this equation. And you might think, oh, since this is true, that will mean that a plus b plus c is equal to 0. But no. So if this is true, then that means this is equal to 0, which means that either this is equal to 0 or this is equal to 0. So we can't just straight away deduce that, oh, then x minus y minus z must be equal to 0. We need to look at both cases first. So first let's factorize this. If we have x cubed minus y cubed minus z cubed minus 3xyz, let's just put this on this side. And we're going to factor it like this identity says. Then it's going to say that x minus y minus z, this is going to be equal to x minus y minus z times, and if we just plug them all in, we're going to get this. Plus, that's because y is 0, and y is negative. Minus yz plus x times z, because z is negative, so it becomes positive here. So, and we're not going to, so from this, we can, using this statement, we can actually try to factor this. Well, this is not in the exact same format as this, because it's negatives here, but we got positives here. But that doesn't matter, we can just factor this. And this is basically just equal to, if we factor in a similar fashion to this, then we get x plus y squared. This is equal to half times x plus y squared plus y minus z squared plus x plus z squared. So, and we already know that x, y, z are positive integers. So what's important to know here is that x plus y squared, the smallest value of this is larger than 0 because, well, this can be the smallest possible value that this can be is 0, but since x, y, z are positive integers, these can never be equal to 0. So this is actually larger than 0, which means that since this is not equal to 0, then x minus y minus z has to be 0, just like you probably hypothesized before. But later on, for the following problems, we have to consider the case when there will be a case when this is actually equal to 0 or this is equal to 0. So in this case, I guess this wasn't equal to 0, so this is equal to 0. But you have to be mindful of that later on. So from this, we deduce that x minus y minus z is equal to 0. So x minus y minus z is equal to 0. So this gives that x is equal to y plus z. And y plus z is equal to, according to this, y plus z is equal to x squared divided by 2. So this is equal to x squared divided by 2. So then x squared is equal to 2x. And then if we just factor that and find the zeros, then we get that x is equal to 0 or 2. But x is a positive integer, so x cannot be 0. So we get that x is equal to 2. Then here we get that, then if we plug it into here, then we get that 2 squared, which is 4, is equal to 2 times y plus z, which means that y plus z is equal to 2. And since y and z are positive integers, the only possible values that y and z can be is 1 and 1. So we get that x is equal to 2, and y is equal to 1, and z is equal to 1. Well, that's pretty neat. So it looks so complicated at first, and we just already found the values of x, y, and z. So we can just plug it into here. And from where we get x times y is just 2, plus 1, plus 2 times 1, 2. And that is equal to 5, so 5 times 5. The square root of 5 times 5 will be 5. So yeah, that's our answer. So from this, well, we didn't really directly use this, but we used this we simplified this, we factorized this in a similar fashion to this. And so yeah, from this we notice that we have to be mindful that if this is true, then this is true. But if this is true, then this might be true, but it can also be we have to also consider the case when this is equal to 0 too. So this is not necessarily true when this is equal to 0. When this is equal, when this is true. Yeah. So that was our first problem. And the next problem is actually a problem from the AMC. A problem from the AMC. Wait a sec. So we're gonna, okay. So the AMC, and since copyright, oh wait, I need to write in blue. Since copyright stuff, I'll just write it here. So from the AMC, determine the number of ordered pairs of integers, m, n. Okay, I'll just provide the information first. So m and n are integers, firstly. Oh, sorry. M and n are integers. And we know that m times n is non-zero. It is non-negative. And we know that m cubed plus n cubed plus 99mn is equal to 33 cubed. And we want to find the number of ordered pairs of integers mn. We want to find mn. Okay, so let's first rearrange this equation because it kind of looks like the sum of cubes and like like 3 times like the product of 3 numbers. So if we just rearrange this first. And we instantly see that, oh, that doesn't even look like a 3. Okay, that's a 33. So we instantly see that this is exactly in the form of this. Because if we say a is equal to m and b is equal to n and c is equal to negative 33, then this is exactly negative 3 times, is equal to 3 times this times this times this. And yeah, so the problem just already gave us this identity here. So using this fact, again, we can deduce that either m plus n, so case 1 is where the sum of these is equal to 0. And case 2 is when this is equal to 0. Well, okay, so for this seems a bit easier. So if we look at this, then this gives that m plus n is equal to 33. And since m and n are positive integers, well, no, are integers, we instantly get that, wait a sec. So we instantly get that there are 34 solutions for m and n if m plus n is equal to 33 and m and n are integers. And we have to find the ordered pairs of m and n. So here we get 34 solutions. And in the other case, it's when this is equal to 0. So this part. So we're going to look at this part because it's the sum of squares, so it's easier to kind of analyze. So if we simplify this, like substitute the values in, we get this, n plus 33 squared. And this is equal to 0. And this is only, since the minimum value of real squares is equal to 0, this is only true when these are all equal to 0. So, which means that m will be equal to n, and m is equal to negative 33, and n is equal to negative 33. So the only solution here is when m is equal to n is equal to negative 33. So that's only one solution. So in total, we have 34 plus 1 equals 35 solutions to this of ordered pairs of m and n satisfying this condition. So yeah, that's practically the same format as the first problem. So that was pretty neat too. Okay, next problem. Okay. Next problem is from the NC math contest. So we want to find the product of all distinct real solutions of the equation. Let me write it. X squared minus 3 cubed minus 4x plus 6 cubed. Oh, my brackets are really messy. Plus 216 is equal to 18 times 4x plus 6 times 3 minus x squared. Yeah, we just want to find the product of all distinct real solutions of this. So, yeah. So again, we can clearly see that if we let a equal to this, so let's just write that down to make it easier. Let's say a is equal to x squared minus 3. And b is equal to negative 4x plus 6, and c is equal to 6, then we see that this is exactly in the form of this. So a cubed plus b cubed plus c cubed is equal to 3 times 6, 18 times 4x plus 6, b. Oh, I see here. They took out the negative and put it here. So basically this is in the form of this. So like the previous two problems, from this we can deduce that either this is 0 or this is 0. So we're going to split it into cases again. So first, case 1 is when a plus b plus c is equal to 0. So this means that x squared minus 3 plus negative 4x minus 6, so minus 4x minus 6 plus 6 is equal to 0. And this gives us that x squared minus 4x minus 3 is equal to 0. And, well, the problem asks us to find the product of all the distinct real solutions. So we can just find this product of the solutions to this equation, which is basically just negative 3. Neat. And case 2 is when this is equal to 0. So when that is equal to 0. And I'm not going to write it here because I'm lazy. So again, like the previous problem, if we want this to be 0, then these squares all have to be equal to 0, which can only be achieved if a is equal to b is equal to c. So a is equal to b is equal to c, basically, if this is equal to 0. So we can just write that x squared minus 3 is equal to negative 4x minus 6 is equal to 6. And if we just arrange things, if we just arrange terms, like if we look at these two and then look at these two, we get that x is equal to negative 3. So we know, so the product of all the solutions in case 1 is negative 3, and we only have one solution for case 2, which is negative 3. So the product of all the distinct real solutions of this equation would be negative 3 times negative 3, which is equal to 9. So the solution is equal to 9. So there we go. So that is basically how very clever ways in which this cubic identity can be utilized to solve many kinds of algebra problems. So yeah, it helps with factoring, it helps with narrowing down solutions and doing some casework to find values. So yeah. So now you probably master using this technique and using this technique to utilize this cubic identity now. So yeah, hope you enjoyed the two videos and now you have a better understanding of how to use this cubic identity. And yeah, see you in my other videos then.